right, everybody, get ready for a wild ride because today we're going deep into the world of optics.
Yeah,
with
the one and only.
Richard Feynman as our guide.
The man.
We've got his legendary lectures on physics.
Yes.
Volume 1, Chapter 27.
Cracking it open.
To uncover the secrets of something we use every day.
We really do.
Is lenses.
It's amazing how much we take him for granted.
I mean, think about it.
Right.
We all know lenses bend light.
They do.
It's how our glasses work.
How cameras capture images.
How telescopes let us peer into the cosmos.
Exactly.
But have we ever really stopped to think
Yeah.
about how we control light like that?
It's pretty wild when you think about it.
How do we make light go where we want it to?
That's a question that's puzzled some of the brightest minds for centuries.
Really?
Oh, yeah.
It seems so simple.
You'd think so.
Light goes in.
It comes out the other side.
Maybe it bends a bit on the way.
That's the key, though. The bending.
So how do we actually do that?
It all comes down to a fascinating little phenomenon called refraction.
Refraction as in light bending when it goes from air to water.
You got it.
Like that classic example with the straw in a glass of water.
Exactly. That's refraction in action.
So you're telling me that same principle is what allows us to create these incredibly precise lenses.
You'd think it'd be that simple, right?
Well, yeah.
Just find the right curve and boom, perfect focus.
Isn't it?
Here's where it gets really interesting. Creating a lens that can perfectly focus light from one point to another, it's way more complicated than it seems.
Wait, seriously, I always assumed it was about finding the right curve, like with a magnifying glass.
Oh, if only it were that easy.
So what's the catch?
Turns out, the perfect lens shape, the one that would give you absolutely flawless focus, is this incredibly intricate fourth-degree curve.
A fourth-degree curve?
Yeah, we're talking serious math here.
So not exactly something you can just whip up in your garage.
Even with all the fancy technology we have today, crafting that perfect lens shape is a monumental task.
So what are we using for lenses then? Some kind of approximation.
Exactly. We found clever ways to get really close to that ideal shape. And the key lies in something called spherical lenses.
Spherical lenses? As in shaped like a sphere?
Pretty much. It's a way more practical shape to manufacture.
I can imagine.
And here's the beauty of it. For rays of light that are close to the center of the lens, what we call paraxial rays, spherical lenses actually work amazingly well.
Ah, so it's all about staying within a certain sweet spot on the lens.
You're getting it.
And I'm guessing it's those pesky rays that stray from the center, the ones that don't play by the rules. Those are what cause distortions in images.
You're on fire today. Those distortions are called aberrations, and they're a whole other rabbit hole we can explore later.
A topic for another deep dive, perhaps?
Definitely. But before we get ahead of ourselves,
Right.
Feynman wants to make sure we understand the fundamental relationship that governs how these lenses bend light in the first place.
The underlying physics.
Exactly.
Always a good place to start.
And he introduces us to something called the lens formula.
Okay, now you've got my attention.
It's about to unlock a whole new level of understanding about how we see the world.
This is getting good.
Oh, it's about to get really interesting.
A lens formula.
Yeah.
It sounds almost magical.
A bit, right. Like a secret code.
So what can we unlock with this formula?
Imagine this.
Okay.
Predicting exactly where a lens will focus light.
No way.
Just by plugging in a few numbers.
Seriously.
That's the power of this formula.
So no more trial and error with different lenses.
Well, trial and error is always part of the fun.
True.
But this gives us a powerful tool to make sense of it all.
I'm intrigued.
Feynman lays it out for us in equation 27.3.
All right, so walk me through this equation 27.3.
It's all about relationships.
Okay, between...
Distances, mainly.
Like how far the object is from the lens.
Exactly. We call that the object distance.
Makes sense.
Then you have the distance from the lens to where the image forms.
Okay, so that would be the image distance.
You got it.
Yeah.
We represent that with sprimes's.
Object distance. Image distance.
We also factor in the curvature of the lens itself.
Right, because a really curved lens is going to bend the light more.
Exactly. And then there's this thing called the index of refraction.
Index of refraction. Okay, now you've lost me.
It's simpler than it sounds.
I hope so.
Remember we talked about light slowing down in water?
Yeah, like how the straw looks bent in a glass of water.
That's because light travels slower in water than in air.
Okay.
The index of refraction just tells us exactly how much slower light travels in a particular material.
So a higher index of refraction means light slows down more.
You got it. Which means more bending, which means a stronger lens.
Okay, that makes sense.
Plug all these values into the lens formula, and boom, You can calculate precisely where that image will form.
No way. And this works for any lens.
That's the beauty of it.
So my glass is a magnifying glass.
The lens in your phone camera,
Even a telescope.
it all boils down to this formula.
That's incredible.
Right.
But I have a feeling it can't be that straightforward all the time.
You're right, there are always wrinkles.
Like what?
Well, sometimes this formula throws a bit of a curveball. Sometimes the image distance, that's as we talked about,
Yeah.
it ends up being negative.
Wait, a negative distance? How is that even possible?
It's not about a real distance, not in the way we typically think about it.
Okay, so what's the deal with negative distances?
It's how we represent something called a virtual image.
A virtual image, like in the metaverse.
Not quite, though the idea of a simulated reality isn't that far off. Think of it this way. Have you ever looked in a mirror?
Who hasn't?
You see an image of yourself behind the mirror, right?
Right,
But you can't actually reach back there and touch that image.
because it's not really there.
Exactly. It's a virtual image. The light rays aren't actually converging at that point behind the mirror.
So it's like an optical illusion.
In a way, yes. It just appears that the light is coming from that point because of how it's being reflected by the mirror.
Fascinating. So a negative image distance in the lens formula means we're dealing with a virtual image.
You got it. It tells us that the light rays, instead of converging to form a real touchable image, are actually diverging, spreading out.
So it's like they're coming from a different place than they actually are.
Precisely. And our brains interpret that as a virtual image.
And the same concept is why swimming pools always look shallower than they are.
Exactly. It's all about how our eyes and brains perceive these virtual images.
Mind-blowing. But you mentioned there was an even more intense equation involved.
Oh, don't worry. It's not that intense.
Okay, good.
It's called the thin lens equation, and it's just a simplified version of the lens formula we've been discussing.
A simplified version. Don't get me wrong, I'm all for simplicity, but why even bother with a more complicated equation in the first place?
Well, the first one, the lens formula, that's the real deal, the one that covers all the bases.
A universal law of lenses kind of thing.
Exactly. But this simplified one, the thin lens equation, it's super useful in specific situations.
Like when we're dealing with really thin lenses?
You got it. Lenses where the thickness is negligible compared to things like the object and image distances.
So like the lens in my glasses.
Exactly.
Because this thin lens equation, it cuts to the chase.
Exactly. It boils everything down to the essentials: object distance, image distance, and the focal length of the lens.
Focal length, right. We talked about that. It's like a measure of how strongly a lens can converge or diverge light.
Right. You remember the focal length is like the lens's fingerprint. It tells you a lot about how it's going to behave.
And we can just plug that focal length right into the equation.
Exactly. It makes calculations a lot simpler.
Elegance and simplicity. I like it. So you're telling me that with just this one number, the focal length, we can understand a lot about how a lens is going to behave.
Pretty much. It's
Yeah.
a pretty powerful concept.
It is, but things must get a lot more complicated when we start dealing with systems that have multiple lenses, right?
You'd think so, wouldn't you?
I mean, take a microscope or a telescope. Those things have lenses for days.
And yet, even with multiple lenses, those same basic principles, they still hold.
You're blowing my mind here. So you're saying the way my eyeglasses work is fundamentally similar to how the Hubble telescope can see those incredible galaxies billions of light years away?
It's all about building up from the basics, right?
Right.
You analyze each lens one by one, like you're following a trail.
Trail of light.
Yeah. You trace the path of the light as it travels through the system.
So each lens is like a bend in the road.
Exactly.
Yeah.
And with those equations we talked about,
The lens formula, you mean?
exactly, we can predict where the light's going to end up.
Even after it's been bounced around by a bunch of lenses.
You got it. And when we're talking about telescopes and microscopes,
And cameras and all sorts of other things.
exactly, we can't forget about magnification.
Right, because lenses don't just focus light, they can make things bigger or smaller.
Exactly.
It's how we get those incredible close-ups in nature documentaries.
And how microscopes reveal a whole hidden world.
Exactly. It's amazing what a lens can reveal, isn't it?
It really is.
So how does magnification fit into all of this?
Well, just like with focal length, there's a formula for that too.
Of course there is.
It all comes down to the ratio between the image distance and the object distance.
So the farther away the image is from the lens, the bigger it appears.
It's not just about absolute distance, though.
Oh, what else is there?
It's the ratio of those distances that matters.
So a tiny object really close to the lens could still produce a small image.
Exactly. even if that image is projected far away.
Okay, that makes sense.
Magnification isn't about making something big in a literal sense.
Right.
It's about how much bigger the image is compared to the object.
Okay, that makes sense.
And here's where things get really cool.
Even cooler than bending light with math.
Oh, this is good stuff. When we combine lenses in specific ways,
Okay.
we can actually multiply their magnifying power.
Whoa. So that's how those compound lens systems work.
You got it. Microscopes, telescopes, they're all about clever combinations of lenses.
That's amazing. But it seems like things would get crazy complicated trying to analyze all those lenses at once.
You'd think so, right?
Right.
But there's a trick.
A trick. Don't tell me. Let me guess. More math.
You know it. But it's elegant math, I promise.
You say so.
It's called principal planes.
Principal planes. Come on, what is this? Physics Hogwarts.
Not quite, though. Sometimes I feel like we're dealing with magic. It's like this.
Okay.
Imagine you can take this whole complex system, multiple lenses,
Yeah.
and condense it down to just two effective planes.
So we're simplifying things.
Exactly. We find the essence of the system.
That's really cool.
It is. And these planes, they represent the overall focusing power of the whole setup.
So it's like taking all those individual lenses and treating them as one super lens.
Exactly. And once you've found these principal planes,
Mm-hmm.
you can basically use those same lens equations we talked about earlier.
No way. So all that complexity, and it still boils down to those fundamental principles.
That's the beauty of physics. There are these underlying patterns that govern even the most complex systems.
It's pretty mind-blowing when you stop and think about it.
It really is, isn't it?
We started out wanting to bend light to our will, and we've ended up confronting the very nature of light itself. It's pretty amazing.
That's what I love about these deep dives. We always start with a simple question, but it leads to some pretty profound places.
It really makes you appreciate the incredible journey light takes, you know? From distant stars to our own eyes, being bent and shaped by these lenses along the way.
It makes you realize there's so much more to the world than meets the eye.
That's for sure. Well, folks, there you have it. Another journey into the depths of knowledge, guided by the one and only Richard Feynman.
The master.
Until next time, keep questioning, keep exploring, and as always, thanks for joining us for another deep dive.